think we can go ahead with these.
Good evening. I moved to this side of the room to avoid feedback with the other microphone. So a few announcements before we get started with the main presentation today. I wanted to welcome everybody to the Science and Hazards of Near-Earth Asteroids. This is a series that's going to be continuing throughout the full semester. Last time we had Tom Zega, and next time we will have a presentation by Danny Delagostina about exploring hazardous asteroids with the OSIRIS spacecraft. And she is an assistant professor and also the PI of the OSIRIS APEX mission. That's the second phase of the OSIRIS-REx mission. Also, please stay until the end because we'll be doing a drawing at the end. Veronica will do the honors, and we had a number of fantastic prizes outside, largely related to the OSIRIS-REx mission. Also, too, for those of you that are here and collecting notes for homework and such, Dolores and Mary will be outside the lecture hall at the end. Please have your work stamped and they'll be able to do that for you. Also a note for the many folks we have online. Thank you to everybody who appeared in person, but we also are running a parallel session online. We will have an opportunity to answer your questions. So please feel free to be able to make those notes in the chat, and we will get to them at the end with our Q&A with our speaker. So with that, it's my pleasure to be able to introduce Dr. Veronica Bray. She's a new associate research faculty in our department, but she has been here for quite some time. Initially, she did her undergraduate degree at the University College London, and then at Imperial College, also in London, she developed her PhD related to impact cratering into the icy Galilean satellites. And after that, in 2011, came to LPL to work with both Jay Meloche and with Alfred McEwen. Since 2011, she's been working with HiRISE, doing many fantastic things with our highest resolution camera in the solar system next door, and also in orbit around Mars. And in addition to that, she's worked on a large number of other spacecraft missions. And so today we'll have a presentation about really the terrifying impacts that might be associated with a Bennu-like body coming directly to our home in Tucson. And please, if you have questions, we'll keep those to the end and we'll be able to moderate those. So thank you very much.
Chris, how are we doing on sound? Good at the back? Oh, good, thank you. So as Chris summarized very nicely, terrifying. I'm gonna do my best job possible to give you an enjoyable end of the world experience, make it interesting and exciting. But this talk is all about the what if. What if an asteroid the size of Bennu impacted Tucson? So an impact of an asteroid is what we term a geohazard. It's a geological hazard. There are many types of geohazards that you might be more familiar with: flooding, severe storms, volcanoes, mudslides. And the way that geohazards are assessed is based on how frequently they happen and how destructive they are when they do happen. So I think one of the ones that we're most familiar hearing about in terms of this separation of frequency versus severity is for earthquakes. We don't need to worry about it very much in Tucson, but most people know that small earthquakes happen relatively frequently. You know, they happen happening all over the place. So small we don't feel them. But then the really big earthquakes, they don't happen as often, but they're obviously much more destructive when they do. So the once in a blue moon geohazard is asteroid impact. They are extremely destructive when they do happen, but we don't expect them to happen during our lifetime, mostly. That's all in the statistics. Okay, so what is an impact event? I figured I'd start off a little bit more generally, before getting very personal with Bennu hitting Tucson. So an impact event, very basically, is two objects in space crashing into each other. It's like a cosmic car crash. And these impacts have been going on throughout the history of the solar system. The planet Earth and all of the other bodies in our solar system are the result of impacts, because impacts don't always have to be destructive. Given the right conditions, so a slow impact, for example, of two similarly sized bodies, they can be constructive. And so right at the beginning of the solar system, we were having lots of impacts because it was all of the clumps of material accreting together to make planets and moons. So impacts are very important to give us the bodies that we live on today, so that the planet Earth. But of course, once the planet Earth is how we like it, we don't want them to happen anymore, because now they're going to be destructive to what we have. Now, impacts happen on all scales. And so the images on this slide are artists' impressions of very large scale collisions, including on the right-hand side, the theoretical, the moon forming impact. So when a Mars-sized planetesimal collided with the proto-Earth, and the debris that was produced as a result of this collision formed our moon. So they are very useful. Usually when I'm working with impacts, they're not planet destroyers in terms of breaking them apart and forming more satellites. My specialities are much smaller. I look at the case of a very large body like a moon or a planet being hit with a relatively small impactor. So a smaller meteor, comet, or an asteroid. So I've got some examples down here for Earth and the moon and Mars. One of the things I also do in my work is I use computer simulation to study the impact process. And I find that these videos of the impact process can be very useful to see, so that you're not just looking at the end product. Oh, it's a hole in the ground. They enable you to have a look at exactly how much rock is moving and how quickly. And so the video that I'm about to show you, I'm hoping that online you can see my cursor. I have layers of rock on this side of the screen, and then you're going to see a variety of blues and reds over here that's basically going to be showing you the amount of damage. So the red areas are where the rock has been completely fractured and moved relative to its initial position in response to the impact of an asteroid. And this little circle here is my simplified asteroid. Notice that we have, this is the impact point, and this is kilometers distance away from the impact point. You're not going, I'm really building this up. I've got you in suspense here. It's like, just press play. The last thing I need to say before we look at this, you're not going to see a circle. You're not going to see that stereotypical hole in the ground. This is more like we're having an impact into a nice layered cake. And then we slice the cake open and we get to look at all of the layers in the cake and the side of the impact crater. So we have vaporization and melting of the rocks. That's all of those little spots flying around in the middle is the vapor. And we have rebound of some of the Earth to form a central peak, which is what we think would happen for this size crater. This is about an 8-kilometer diameter impact crater. If we back up, you'll also see that there's ejection of the rock out of the crater cavity and off into the surrounding areas. So we see these resultant impact craters all over the world, but we don't see very many of them. And that's because Earth has a really good weather system, which starts eroding these craters. We also have active plate tectonics, which remove the rock that these craters may have formed in. We also have a lot of sea cover. You'll notice on this map of all of the different craters that we do have identified, they're mostly all on land. And that's because they're very difficult to find in the sea. They're usually covered with layers of sediment. You'd have to find them in seismic profiles. And you really have to find them by accident, really, if they're in the sea. One of the better places to look if you're wanting to see how often the Earth has actually been hit by asteroids and comets is to look at the moon. All of the circles that we see on the moon from the Earth are the scars of ancient impacts, and it's completely covered. On Earth, some more evidence that we have for past impacts is evidence of global catastrophic changes, ejecta layers, iridium layers, that are all pointing back to the demise of the dinosaurs as the result of a large impact, which happens to be this blue dot on the Yucatan Peninsula. That's the Chicxulub impact crater. I would not be doing my job if, while giving a talk in Arizona, I didn't encourage you to go up the road near Flagstaff and go and visit your very own meteor crater. This is a fantastic example of when an asteroid has hit planet Earth, because it's small enough for you to see how big it is. A lot of impact craters, they're so large, they just look like hills in the distance. You wouldn't know that you're standing on an impact crater. It is something embarrassing that happened to my undergraduate class. We'd had 4 years of specialist planetary science training, and in the 4th year, we were taken on a field trip to the Reese crater in Germany. And we were stood on the rim of the crater, and they asked us which way the center of the crater was. And we're specially trained, like we're supposed to be doing this, and 50% of us pointed out away from the center of the crater because it was so covered in farmland. There was a town in the middle. You couldn't really see that it was a crater anymore. But Barringer meteor crater near Flagstaff, it's a really good example. And it was formed by a relatively small iron meteoroid. So about 50-meter projectile formed about a 1-mile crater. Oh, and apologies for the mixing of my imperial and metric units. I know some people like feet, I think in meters. And so I tend to get them mixed up these days. So apologies, I know it might be annoying. And an example of this relatively small impact, I've listed the energies at the bottom here. So the Barringer meteor crater was 30 million tons TNT equivalent. This was a gigantic explosion, dwarfing the Nagasaki and Hiroshima nuclear explosions by orders of magnitude. And this is a tiny little crater. So if we start looking more towards Bennu, that's 15 billion tons of TNT equivalent. And even that, if we start looking towards the impact that killed the dinosaurs, I don't even know what this number is. It's too many zeros. I heard that. Somebody knows. Okay. So we do have more evidence of impacts, incoming impactors, would-be impactors in the present day. So we had a lot of very large impacts early in the solar system, and over time, the process of accretion is bringing these more and more little bits of space to us, and the planet Earth is getting slightly bigger and bigger. but we swept up all of the large pieces for the most part. Not completely, but for the most part. And so these days, most of the incoming debris is relatively small and they can't make it through the Earth's atmosphere. So instead of impacts, we get airbursts, where a meteoroid heats up because of the friction with the atmosphere and it explodes. Now, that doesn't sound too bad until you look at the effects of an airburst. So I have two examples here. The top left is the Tunguska airburst in 1908. This picture was taken in on a field expedition in the 1920s, and miles of trees were just felled like this, with all of their leaves ripped off as well. More recently, the Chelyabinsk airburst, it was videoed. That's what's up in your top right. And then I don't want to imagine what it was like standing in this hallway outside an auditorium. So we're safe in the auditorium. That's somewhere over this side, behind some doors. But if we were in the foyer and there were glass windows, that's a lot of glass suddenly flying at you because of one of these. And so even though it doesn't feel like a big threat to have something come in and blow up in our atmosphere, these can be really devastating. This is a map of all recorded airbursts over about a 10-year period. So we are getting incoming debris coming at us and exploding in our atmosphere. So that's the small side of things. And the example of how large these incoming meteors were is shown in the circles here. This is the Tunguska event. This is the Chelyabinsk event, relative to the Eiffel Tower and the Empire State. So how big is bad? How big do we need to get before we're going to get through the atmosphere and actually cause an impact crater? It does depend on the properties of the incoming material. If you have something really dense and cohesive, like an iron meteorite, a smaller one could get through. Whereas if you have something that will break apart more easily, like a stony meteoroid coming in, it'll break up further up. But I've included some examples here. If at the top of our atmosphere, the meteor is only 5 meters, it won't get further in than about 42 kilometers up. So really high up detonation in the atmosphere. And I should mention, just in case the use of different wordage sounds a bit strange, before a meteor enters our atmosphere, it's a meteor. Once it enters our atmosphere, I'll start referring to it as a meteoroid. And then the bits that you find left over from an airburst or from an impact when you find them on the ground, those are the meteorites. So if we have a large meteor, 70 meters at the top of the atmosphere, that'll reach just over the top of Mount Lemmon, about 3,000 foot above the top of Mount Lemmon when it bursts, detonates. I don't know whether I can use the word detonate, but it really feels like a timed bomb about to go off. We need to get about to 100 meters in diameter before the meteoroid would reach the surface. So now let's get around to Bennu. So compared to these devastating airbursts. So Bennu is about 500 meters in diameter. It would reach the ground. And so this brings us on to our main topic this evening. What if? What would happen if Bennu hit Tucson? So if Bennu hit Tucson, sorry, let me give you my reasoning. I usually like to start my end of the world scenarios up at meteor crater in Flagstaff. But I figured Bennu and the OSIRIS-REx mission are very personal to LPL, so I figured, and we're all here tonight, so we are the yellow star, and I'm going to have Bennu hit Park Place Mall. No offense to Park Place, I like it. I was going to have it hit Elcon, but then the talk would have been too short because we'd have been obliterated very quickly. So a little bit more dramatic if I push it off a little way to Park Place. So that is the size of the impact crater that Bennu would create. So Park Place Mall is gone now. I hope you did your holiday shopping already. The Bennu asteroid would not reach the ground intact. It would be somewhat disrupted by the atmosphere, but it's coming in at 17 kilometers per second. So the disruption isn't really going to allow it to disperse particularly. So we're still expecting most of those impactor pieces to impact in about a kilometer radius and give us what a normal impact crater would look like. So about 6 kilometers across. We're going to be talking second by second through what would happen if this occurred at Park Place. But something to note before we start is that the formation of an impact crater of this size would take about 80 seconds. So the explosion of Bennu, the release of its kinetic energy, would open up a transient cavity. So the ejector would start moving away from the impact point. All of the rock would be moving kind of in a fluid-like manner over this time scale. You don't normally expect rocks to move 6 kilometers over just seconds. But over the course of 80 seconds, we'll have our crater forming. We don't need to worry about that because we've got bad stuff coming our way. So when I move the slide over, it's going to show you second by second what's about to happen to us in the next minute after impact. The reason I'm kind of talking you into the next slide is that the first thing that will happen to us happens in 0.3 seconds, and I don't speak that fast. So almost immediately, we're going to be subject to a thermal pulse, and I'll get into the horrible details of that later. And then just 2 seconds after impact, oh, my timing's off, ignore the clock in the top. Whoops. 2 seconds after impact, the earthquake's going to reach us. And then we've got a little bit of chill time. After this big earthquake, we've got about 30 seconds to burn before our blast wave arrives, this massive sweeping wind that's coming out away from the crater. While we're still dealing with the aftermath of that, we're then going to receive the impact ejector. All of that rock that was thrown out of the crater is going to come showering down on us about 44 seconds after impact. The final resting place of the ejector will cover this entire area. Okay, so a little bit more detail for all of those nasty steps. The first thing that we're going to experience is the thermal pulse. This is a release of thermal radiation. And I'm going to start talking about all of our friends and relatives that might be up in the Phoenix area. So this, and in this yellow region, they'll be able to see the fireball. So from their perspective, it's going to look reasonably similar to this nuclear test video here. They'll be able to see the fireball, and they'll also experience a notable but uncomfortable heat for about 1 minute. I mean, okay, we're talking about them being up in Phoenix, so it's yeah, enough. But even worse, even more so than usual. We don't need to feel sorry for them because we are within this region. So The orange area, the deep orange area marked on this map, this is where clothing ignites. 3rd-degree burns, paper, wood, plywood, trees, grass, overly dry hair will all instantaneously ignite. And for us here at LPL, we would see the fireball as a result of the Bennu impact as 103 times larger in the sky than the sun. We will also be experiencing about 1,000 times more heat than we get from the sun. Luckily, we're in an auditorium. It's still going to be horrible, but I expect we'd still probably be on fire, but not as sure as people walking around outside. So for the good of the talk, let's assume we're all safe in here. Everyone else outside is on fire, but we can survive till the next step. Useful for the talk. The only visualizations that I can give you for extreme events like an impact are from nuclear test sites. So the next video that I will add on to this slide, I figured I'd give a warning. It's of a school bus in one of the nuclear test sites. So you'll see what this school bus experiences in response to a thermal pulse. So I'll move on to that. If you don't want to see it, look away and I'll let you know when it's clear. I hope the prize books aren't getting in the way of your view of this horror at the front. So this isn't wood or paper or hair. This is metal and paint instantaneously burning in response to a thermal pulse. And so this is what we can expect around here. It's not so much that it doesn't set fire, it just goes from unburnt to burnt. Okay, moving on to the next slide. So that's our first second that we have to enjoy. So if we suspend our disbelief and we imagine we're all still alive, we can experience the second nastiness coming towards us, and that is the impact-generated earthquake. So the energy released by a Bennu impact on Park Place Mall would produce a 6.9 on the Richter scale, fairly big, but not the largest earthquake that America has experienced or the world has experienced. But what we need to consider more than the Richter scale magnitude is the modified Mercalli intensity scale, and this varies with distance. So if you're closer to an earthquake event, then of course it's going to be worse for you. You're going to be higher on the Mercalli scale. So statewide, everyone's going to experience a Mercalli scale of 3. So they're going to notice vibrations like a heavy truck going by. So if you're standing next to a highway anyway, you might not notice it. But if you're in a quiet area, you'll notice some rumbling and wonder where it came from. The light green circle, you'll get to a Mercalli scale of 5. So this will cause the cracking of some windows as the foundations of each house moves slightly in response to these earthquake waves coming. Unstable objects will be displaced. I've heard this best described as like the china cabinet, the crockery, clinking on its shelves, or cutlery rattling in drawers. People will be woken from sleep, perhaps. My husband's a really heavy sleeper, so I reckon he could make it through. But most people, I think, will be awakened by a Mercalli scale 5. However, we don't need to feel sorry for them because we're down here in the green area. So the dark green here shows scales 7 and 8. But of course, we're closest, so we have a Mercalli scale of 8. And I've got some examples of the sort of destruction that we can expect local to us. These are similar Richter magnitude earthquakes The first at the top is what would happen to road bridges. It looks survivable depending on where you were on or under that bridge at a particular time. Harder to survive is when you're indoors. So we were lucky being indoors for the thermal pulse to pass us by, hopefully. But most buildings in Tucson, Arizona are not designed to withstand hard earthquake activity. So I can't vouch for our survival level in this room. This image in the bottom left is an example of both ends of a building collapsing and sandwiching the second floor. So again, a lot of destruction, and it'll be luck as to whether we make it out. Because I don't think that most buildings in Tucson are designed to deal with earthquakes, I think there'll be considerable damage, partial to full collapse of different buildings in Tucson, depending on how well they're built. We can expect chimneys to fall off if the house itself isn't also falling, walls, heavy furniture overturned, and it goes without saying that it's difficult to stand at that point. So we've got a break now. We've got 28 seconds of nothing. So we've been burnt, we've had our earthquake, and at the 30-second mark, now we have my favorite of the impact hazards. And it's my favorite because air and air movements don't look like they're do you much damage. So you wouldn't necessarily see it coming, obviously, but it does a lot of damage. So all of Arizona is going to experience a 10-mile-an-hour wind and a 60 decibel bang. Now, we had 10-mile-an-hour winds today. It's nothing special. A 60 decibel bang is just above conversation level, depending on the loudness of your friends and the how loud you speak, but we tend to speak at about 50 decibels normally. The light blue area here that includes Phoenix, they can expect a 40-mile-an-hour wind and 70 decibel bang. Now, this isn't just a 40-mile-an-hour wind like we're used to for like a hurricane. There is a distinct pressure wave that accompanies this. So the 40-mile-an-hour wind in this scenario is going to shatter some windows all the way around to Phoenix. The medium blue area surrounding Tucson, that's going to get even worse because we're getting closer to that impact point. 90-mile-an-hour wind, 80 decibel bang. This will have the capability of knocking down some poorly constructed buildings. But of course, just like all of the rest of them, we don't need to feel sorry for the rest of Arizona because we're right next to it, 6 miles away from the impact point. And we're going to have a 2,130-mile-an-hour wind and a 124 decibel bang. I don't have any examples for you of what this would be like. So I've listed the things that would happen. I mean, it goes without saying that if the 40-mile-an-hour wind can shatter some windows, then we will expect windows shattering. We won't really be concerned about that because the house won't be there anymore. Depending on how well it is anchored to its foundations, you might have had it blown away, toppled over, collapsed, various amounts of building collapse or distortion. We can also expect anything that isn't rooted to its foundations, anything movable like a car or truck, to be very displaced. So when I'm saying very displaced, blown into California level of displaced. But they will also be largely and grossly distorted. So that's the technical jargon that comes out of the code when I'm looking for the impact effects. The real world way to describe it is if there was a telegraph pole or a street lamp that somehow was still standing and your car was being blown by 2,000-mile-an-hour winds, it would wrap around it. So that's what we mean by grossly distorted, is you wouldn't really be able to tell which car was which anymore because they would have been kind of jumbled together. And then just like the Tunguska air blast, we would expect all trees to be blown down and stripped of leaves. I do have another video of a nuclear test that I'm about to add. So here we go. So this is a very short repeating video of the airburst. It's very short because the camera was destroyed as soon as the airburst reached it. Some of you may have already noticed that we can see the fireball in the background. Oh, sorry, I should be doing this for the online people. We can see the fireball in the background, and you can notice telegraph wires in the front that are already burning because they've already experienced the thermal pulse. So they're already on fire. And then they're blown out like a birthday candle by the air blast. So if you're an optimist, you're no longer on fire, and that's the good thing about an air blast. Okay, accompanying the air blast is a very loud bang. We will expect 124 decibels here at LPL if Bennu hit Park Place. I've got a couple of examples of the noise levels. 90 decibels, 15 minutes of that will give you some bad ear damage. That's like going to a demolition derby truck show and not wearing your earphones for 15 minutes, or sitting on your lawnmower. If you have one of the driving lawnmowers, don't do it for more than 15 minutes without your ear defenders. At 110 decibels, we can expect hearing damage in less than 2 minutes. And we do expect pain and instant hearing damage at 120 decibels. So we would be injured by this bang associated with the air blast. When I was choosing where to have Bennu hit, like I said earlier, I considered putting it at Elcon Mall, and I was quite amused to see that the noise that we would receive would be 137 decibels, which is the same as the KISS tour. They managed to be louder than Bennu impact at Park Place. The reports from this tour have mortar falling down from parts of the stadium, and they structurally damaged the stadium. I've been giving kind of end of the world talks for a while now, and I have not found a more up-to-date pop culture reference. If anyone has one, please email it to me, but I'm pretty sure we're not going to beat KISS. Okay, so the next thing that we need to worry about, so let's take a moment. There's a lot of depressing stuff happening, so I like to take a break before the last one and just kind of recap. So everyone outside is on fire. If LPL was really well built, we're probably okay with the earthquake. We'll all have fallen to the floor. But then the air blast, we wouldn't have survived that, to be fair. But if we can suspend our disbelief and we're somehow not on fire and not crushed or not blown away, the next thing we need to worry about is the impact ejector. I'm just going to show you the same video as I showed you earlier, but pay attention to the rock that has been thrown out now. This is showering down all over the area surrounding the crater. So zooming out to have a look at what's happening to Casa Grande, and they will have a very modest coating of just a 1 centimeter thickness, but it's an average rock layer. This isn't uniform dust that will settle on them. It will include golf-sized chunks. This is a photo of Gulf-sized hail for comparison. The darker area here that we are of course in and having to worry about has a coverage of more than 10 centimeters depth at its outer limit, so at this edge of the gray circle. And of course, the closer to impact you are, the worse this is going to get for you. So just a reminder of where we are. The crater is forming only 6 miles away. At 44 seconds, the crater isn't fully formed yet. It's still got another 40 seconds to go before it will look like what I'm about to add. This is an impact crater of about the same size on Mars. This is Steinheim crater on Mars. We do have a Steinheim crater on Earth as well, different size, different age. And so you can see there we go. You can see the crater rim. You can see the central peak, that central uplift, and then the terraces where the rim has slightly collapsed. And then all around it is the ejecta blanket of thrown out rock. Now this ridge here is the main deepest portion of the ejecta blanket, is here. And as you get further away from the impact crater, the ejecta blanket gets thinner and thinner. We're right on the edge of the continuous ejecta blanket. And so my estimate for how deeply buried we're going to be is somewhere between 6 and 18 meters depth. So you can see that the edge of the ejecta blanket kind of undulates a little bit. So if we're feeling optimistic, let's go. If we're feeling optimistic, we're only buried under 6 meters of rock. So if LPL was still standing at this point, we do need to start worrying about things like roof collapse. And if you were ever planning on digging your way out of the rubble, you do now have an additional 6 meters to worry about. So hopefully the timer will start and it'll run smoothly into time. So just to recap our blow by blow, 2 second mark, we get our earthquake, and then we're going to be hit in the face at 30 seconds by an air blast, quickly followed by the ejecta. Of course, we're already on fire since 0.3 seconds before this. And so the time that we have to enjoy after Bennu hits Park Place Small is very small. But wait, there's more. Not for us here in Tucson. We don't need to worry about tsunamis, but most of the earth is covered in water. And so if we stop thinking about just Tucson and we start thinking about the rest of the world, most impacts that will occur are going to give us the earthquake, the thermal pulse, the air blast, the ejecta, and a tsunami as well. And so I have a couple of videos with a deeper water layer. I'm sorry, it's colored light brown instead of a useful blue, but you'll see how high they get. This little tick here is 1 kilometer's height above the surface of the ocean. So you have a significant outgoing tsunami, and it doesn't stop there. You don't just get one. As the water column oscillates in the middle, like the sea goes back in to fill the gap formed by that crater, you're going to get tsunami after tsunami coming out. This is a simulation just to show the expanding tsunami wave along a shoreline. This isn't on Earth, this is a Mars project. So we have an impact occurring here, and the red and blue waves show you that tsunami front. So like I said, it's not just one tsunami that occurs as a result of that impact crater, but it's also not one tsunami that you need to worry about either. Every time it hits another section of shoreline, it will reflect off it. It might cause another landslide, which then sets off another tsunami. So this is just utter chaos. Oops. So how do we prepare for this geohazard? This is the last bit of the talk. I figured that I didn't want to leave you on a sour note, so I'll, get a bit happier at the end. Oh, after this slide though. So how do we prepare for this? I think you know now that we've spoken through how destructive these are, there's nothing we can do. If we're in the wrong place at the wrong time, there's not much we can do. I mean, the best you could hope for is that maybe if you had a nuclear level bunker, you would be safe. But remember, there's a gigantic earthquake coming your way, and that's not going to leave your bunker alone. So I think the best solution that has been agreed upon by most impact scientists that are worrying about this geohazard is evacuation. There's a lot of big brains out there that will be able to look at the incoming trajectory and work out which city it's going to hit. And the only hope we then have is that we've seen it with enough time to evacuate that city. But okay, now we can pick up and be a bit more positive. We can't do anything if it happens, but we need to prevent this. And so this is where this seminar series came to be. It's why OSIRIS-REx is happening, is we're working out how to prevent airbursts and impacts in future. And the way that we do that is getting to know our enemy on this. We need to know where they are, when they might impact us, what they're made of. And once we understand what they're made of, we can better know how we might be able to stop them from hitting us. So I'm going to go through these last slides quite quickly so that we have time for questions, but also each of these is a talk in itself. The first questions, where and when. So there's missions and there are projects. There's Tucson's own Catalina Sky Survey that's mapping the locations and the orbits of various different bodies in the solar system that we might consider to be a threat. So on this visualization, you have the Earth in the midpoint. All of the pink ones are dangerous. All of the yellow are main belt asteroids. We don't expect them to come out at us at all. And so there's a lot out there that are Earth crossing, and we do need to keep an eye on. And we're doing our best with the Catalina Sky Survey and other work. The what. So we need to know what they're made of in order to get them to go away. Part of this is meteorite studies. So working out, how heavy they are, how porous they are, how easily they can be broken. But there is a little bit of survivor bias with this. All of the meteorites we found are the leftover survivors of impact or airburst. So they're probably very strong compared to if we think about the main body that broke up in the atmosphere. So we also are looking towards actually going to these places, going to comets, going to asteroids. There's been a lot of missions that have already gone and visited. We want to observe, we want to collect samples, which of course OSIRIS-REx recently did, and we want to interact with them. Deep Impact, for example, has collided with a potential meteor. Okay, that brings us on to the last bit, the how. So once we know what these things are made of, we kind of understand them a little bit better. We have a hope of deflecting them. We're not going to be able to destroy them because probably all we make is, instead of one incoming asteroid, have 10 or so. There are a lot of theoretical ideas for what we could do. One of them is a solar sail. I've seen solar sails used in slightly different ways. This is an example from ESA. I've seen these tethered to an asteroid so that the solar wind can pull it off course slightly. More commonly, I've seen a solar sail put into orbit around an asteroid to stop the sun heating up part of it. And as soon as you get a weird temperature difference on its surface, it affects its spin, also puts it off its normal trajectory. Gravity tractors. This is the idea that we would be capable of sending a massive enough spacecraft to basically park next to an asteroid and just gently gravitationally pull it off course and take it out of the line of an Earth interaction. Laser ablation. This is the pew 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 of all of these theoretical suggestions. This is literally vaporizing sections of the asteroid surface, all of the volatile minerals in there, so that we get ejection of material. It'll act as a thruster, pushing it off course. And then, of course, most recently, the DART mission is an example of the impact how. The idea that we can impact into an asteroid or a binary asteroid pair. We can affect their rotation around each other, and that's also going to affect its orbit and move it off course. For all of these, we need years lead time. We'd need to see it coming, and we'd need enough time to affect its orbit enough to just miss us. So studying the asteroids is what the next seminar talk is going to be about. Please join Danny for that one. I'm sure it's gonna, I'll be there. And thank you for joining me this evening for the what if. Thank you. And I'm sorry, I've waffled and we have 5 minutes for questions. Please email me if we don't have time.
We'll start with the questions in the room, and then in a couple of minutes, we'll take questions from online as well. So we actually have speakers up on the ceiling, so it's a fantastic addition. Folks will be able to see you online without the microphone, but if there's any ambiguity, we can repeat the question. So any questions? Yes.
This is a simple question. How tall is the Kuiper building?
Oh, I don't know.
You said 18 meters as the upper limit of the ejected blanket. So I'm thinking that's about a 5-ish story building. Would that be taller than the Kuiper building?
I don't think it would be taller than the Kuiper building. I'd say that this room is 3 to 4 meters high at this end. So the room would be filled up. I don't think it would cover the building. So yeah, maybe we can come out the roof in the middle.
Wait, so like, has an asteroid impact ever occurred during like human history, like for like the past few 100,000 years? Do you know of any asteroid impacts that happened during that time?
Oh, there's a lot of argument actually over a few impact structures. One of the extinctions of like the woolly mammoths, saber-toothed tigers, which would have occurred while humans were around on the planet. There is an impact crater under the ice of Greenland called Hiawatha, which some people have suggested that might have been the cause of it. A lot of argument over the age of the crater, of course. Thank you.
Can the objects that come in from the side of the sun, can they be detected?
So that is, we have trouble seeing incoming projectiles if they're very fast, very inclined orbits or very oblique orbits, if they're coming from the sun. And we were recently surprised by a close call that we weren't expecting.
Wouldn't it come in between the moon and the earth?
Yep.
Yeah.
Close enough to buzz a few satellites. And yes, the Catalina Sky Survey and other efforts are doing our best to see as much of the sky as possible, as often as possible. And I think it's, I'll put the plug in. I think it's a good plug for further funding of such efforts that we missed that one.
Other than the impact crater, would there be any evidence like millions of years down the line to like determine like if this a Bennu hit or not? Like how like the dinosaur meteor caused iridium, like a layer of iridium? Would something similar happen?
Oh, yes. We have several different ways, millions of years after impact, of finding that the whatever scar we found is an asteroid impact. There's certain rock types that we only expect to be produced by an impact. Things like shatter cones have to have a particular amount of pressure in order to generate them. We also expect impact melt, so the rock will have been melted as well. And so millions of years from now, when Tucson is naturally under lots of sediment, somebody could drill down, get a sample, and like, hey, there's impact melt in here, maybe with iridium signatures, showing that it was something not of this world that hit us.
You talked about the damage that asteroid do to our place. Does angle projection have a different effect?
Absolutely. So all of the numbers I gave you today were based on a straight down impact. But that's not the average. The average would be a 45-degree impact angle, but then I didn't know whether to have it away from us or towards us. So I felt it a bit more fair that I give it, a straight down impact, but it really would affect what we're seeing. For example, Bennu would break up more in the atmosphere. It still would reach the ground. It would form a 5-kilometer crater instead of a 6-kilometer crater. So it's still going to completely mess up LPL and the surrounding Tucson area, but slightly differently.
Still will die.
Yeah, you mentioned the methods that they were striving to change the trajectory of incoming asteroids. Is there a risk involved that they might make the trajectory or raise the risk of the impact?
Excellent question. I believe that one of the reasons most of these are still theoretical rather than tested at this point, money, obviously, to fund the space missions, but also the worry of making a mistake in the wrong direction and increasing the chances of impact. So yes, there is a risk, but that's one of the reasons that these projects are few and far between and extremely carefully thought out. Lots of big brains on the DART mission.
Before taking a question online, I'll selfishly pose one myself. In one of the nuclear test videos that had the fireball, and there was after the thermal pulse had come and affected the telephone lines or the power cables, there were these two trees that seemed to like be translated, just sort of dancing across the landscape. But what's happening there?
This one?
Yeah, they're just.
Oh, they're being blown away by the air blast. The dancing trees.
But they're not lifting off the ground. It's just it's such a weird movement. I didn't know if the roots are still holding them in the ground or it's very bizarre.
I have to admit, I've been surprised. I think you're right that there might be something to do with weirdly strong rooted trees, because all of these trees are felled, not blown out of the area. And so I have been surprised actually with the strength of tree roots when it comes to air blasts.
Okay, well, thank you. And let's see, do we have questions from online?
Yes, there's two questions. If Bennu hit the middle of the Atlantic, would it affect the climate in Tucson?
So if we're talking about the middle of the Atlantic, I think I'll be kilometers off on this, and I'm sorry. I think the sea depth is 3 kilometers. So either 3 or 6 kilometers. Either way, I would not expect Bennu to make much of a crater in the seafloor. I don't think we'd have any ejector, for example, so there wouldn't be any rocky ejector coming our way. There would be a large tsunami that is about to hit Europe, America, South America, like Africa. I don't think it would affect the climate.
And the other online question is, how is asteroid detection evolving for spotting likely impactors?
The longer we observe, the more we see. Part of this is because in order to find something out there that's moving, you need to be observing long enough to see it move. And then you need to be observing for even longer to get an idea of its orbit. Is it on a steeply inclined orbit or an elliptical or a circular? And so we have a better grasp on what's happening in the asteroid belt between Mars and Jupiter because it's closer, they orbit the sun faster, so we can track them more readily. One of the things that we are not as good at is looking towards the Kuiper belt, so beyond Neptune and all of the comets that come from that region. So work is evolving because we've got better telescopes, better higher resolution cameras looking out there, looking for things, and we've been observing for longer. So we're starting to see more.
One last question from the audience here.
I have a question. With the asteroids that you've been able to like study or like collect, have you been able to determine like how old they are? Like if they've been around since our galaxy has been around, or are they even older than that?
Oh, wow. The question was for the meteorites that have been studied, how old are they? Have they been around since the beginning of the solar system? That's an entire lecture series in itself. It's an amazing subject. I encourage you to ask Dolores the same question. She's at the back of the room. She's a meteorite specialist. When we've been looking at different meteorites, they do contain pre-solar grains and parts that we think are from the very birth of our solar system. They also include later, like some meteorites have more developed crystals that might have been produced in like a large differentiated planet, for example, and the iron meteorites might have been part of a planetary core. So yeah, they're from all over the history of our solar system. Thank you.
Great. Well, thank you very much. Before we thank our speaker, just a couple of things. First, please, if you have additional questions, feel free to be able to come forward or to be able to send an email to Veronica. Also, if you're interested more in her research, she had an extremely high profile paper that came out about a previously undiscovered, very difficult to detect impact crater located off the west coast of Africa. That was published in Science, and so definitely take a look at that, or if you have questions, you can ask her about the process of hunting for some evidence of these large impactors. And lastly, if folks do need to be able to have their stuff signed, we can do that outside. And I think we will thank our speaker and then do the draw for the door prize. So let's please thank Veronica. So Dolores and Veronica, to do the honors with the prize. Prize is.
Yeah.
How many? 7182195. Oh dear.
Okay, well,
I know him, it's not fixed. Hi, Joe.
mention the prize first. Okay, would you like the patch? Okay, Osiris Rex patch. Next, we'll do a sample return capsule.
Not a real one.
Oh, it's me. Clean one.
Oh, 7182212.
I have it, okay.
That's this one.
Very good. I'll take your word for it. Okay, now we'll do a scorched sample return capsule.
Oh, somebody put both of their. Oh, more than one person put both of their tickets in. Oh dear. Well, all right. 7182224.
Okay. Let's do a cup next.
Cup. The next one for a cup is 7182192. Seven one eight 2192.
This is the laboratory that will analyze the Bennu samples.
Grab the
That
second
one's
one.
okay.
What's next?
Next, we'll do another sample return patch.
7182227. Two.
Okay. Okay, how about another patch?
Okay, another patch. 7182205.
Oh, all right. You got one last time. Oh, all right. Well, how about a post? Go with your patch.
What's next?
So next, we have two more patches. We can save those for the end. How about our Kuiper biography?
7182218.
All right. Next, we have one of the first publications about OSIRIS-REx and asteroid Bennu, signed by Dante Loretta, the principal investigator.
7182198. 2198. Oh. Okay. 7182226. I've already got the second one.
Then next, we have the Tom Garrels biography.
7182222.
You got it?
Yeah.
Congratulations.
Thank you.
Sure. Okay, we'll save the Bennu book for last. So how about two more patches? One more patch, sample return.
Okay, so three. Three
Three
things.
total.
Okay. Okay, first patch, 7182213.
All right. Okay, one more patch. Oh,
Okay.
yes, one more patch.
Last patch, 7182204.
Very good. Congratulations.
When just to amp this one up, this was written by Dante Loretta and Brian May of Queen. So Brian does a lot of stereo work with space imagery.
It's a beautiful book and has a lot of detailed information about the mission.
Okay, this is 7182196. 2196. The suspense. Okay, last
Wow.
call, 2196. Okay. 7182230.
Very good.
Yeah, he was looking around. going, yeah, yeah.
Congratulations.
Okay, thank you.
Actually, there's two posters here. I don't know.
Oh, okay. We can pull
Bonus
another number.
prize.
2220. 2220.
Microphone may be dying, but that's okay. I'll speak up a little bit. So also too, if folks need to use the restroom and you're not familiar with the building, if you come out and then on your right, you'll be able to find the restroom. And service elevator. And again, our next presentation in the lecture series will be you'll have seen that on November 15th. Thank you, speaker once more. Thank you.